When calculating volumes of revolution, the disk and washer methods aren't always the most efficient. Today, we explore the shell method, specifically focusing on how to handle rotation around shifted horizontal axes. Understanding this allows us to solve complex solid geometry problems by nesting thin cylindrical layers, much like the layers of an onion. We choose the shell method when the boundary functions are easier to express in terms of y, or when rotating around a horizontal axis requires us to use rectangles parallel to that axis. This method simplifies the integration process by avoiding complex inverse functions that might arise with disks or washers. A critical rule to remember: in the shell method, the variable of integration is always perpendicular to the rectangles. For any horizontal axis of rotation, whether it's the x-axis or a shifted line y equals k, we must integrate with respect to y. This is the opposite of the disk method's logic. The core challenge with a shifted axis is redefining the radius. The radius is no longer just y. It is the absolute distance between our differential strip at height y and our axis of rotation at k. This distance is expressed as the difference between the two values. Conversely, if the axis y equals k is above the shaded region, the constant k is larger than any y in the interval. In this scenario, the radius becomes k minus y. Always subtract the smaller value from the larger value to maintain a positive radius for your geometric solid. The height of our shell is the horizontal width of the strip. If the region is bounded by two functions, the height is the rightmost function minus the leftmost function. If it's bounded by the y-axis, the height is simply the value of the function x equals f, y. Putting it all together, the volume equals 2 pi times the integral from c to d of the radius times the height. By substituting our specific distance expressions for the radius and our function expressions for the height, we create a definite integral that represents the total volume. First, identify the components. The radius is the distance from y to -1, which simplifies to a y plus 1. The height of the shell is the distance from the y-axis to the curve, which is simply a y squared. Our limits are determined by the y values of the region, 0 to 2. Now we set up the integral. We multiply the radius y plus 1 by the height y squared, resulting in the polynomials y cubed plus y squared. Using the power rule for integration, we find the antiderivative, y to the 4th over 4, plus y cubed over 3. Evaluating from 0 to 2, we plug in our bounds. For plus 8/3 equals 20/3. Multiplying by our constant 2 pi, we get a final volume of 40 pi over 3 cubic units. This represents the total space occupied by the solid. Let's try one where the axis is above the region. We are rotating the area under x equals 4 minus y squared around the line y equals 3. This will create a solid with a large central cavity. In this case, the radius is the top line 3 minus the variables y. The height is the functions 4 minus y squared. Since the region is in the first quadrant and bounded by the x-axis, our y limits are from 0 to the y-intercept at 2. Expanding the integrand gives us a 4-term polynomial. Integrating term by term, we get 12y minus y cubed minus 2y squared plus y to the 4th over 4. We are now ready to evaluate this at our boundaries. Plugging in 2, we get 24 minus 8 plus 4. This simplifies to 12. Multiplying by 2 pi, the final volume is 24 pi. Notice how the setup was the most critical part, the rest was just polynomial calculus. What if the region is bounded by two curves? The height of the shell is simply the right curve minus the left curve. The radius logic remains the same, distance from the axis of rotation to the representative strip y. It is helpful to compare. For a horizontal axis, shells use dy and washers use dx. If your functions are already solved for x, shells are usually much faster because you avoid having to square binomials or solve for a y. A common error is incorrectly adding the shift to the radius. Remember, the radius is a distance. Always visualize the gap between the axis and the strip. If you get a negative volume, check if you subtracted your radius or height terms in the wrong order. Unlike the washer method, you don't need to subtract an inner volume from an outer volume. The shell method builds the solid layer by layer, starting from the radius closest to the axis and ending at the furthest, naturally accounting for any central void. To master this, follow these steps: sketch the region, identify your y-limits, determine the radius as the distance from the axis, find the height as the width of the region, and set up your 2-radius height integral. Consistency is key to avoiding errors. Test your knowledge. If we rotate the region bounded by x equals 1 over y and the y-axis, between y equals 1 and 3, around the x-axis, y equals 0, what are the radius and height for the shell method? The shell method is a powerful tool for finding volumes, especially when rotation occurs around shifted axes. By focusing on the geometry of the cylindrical shell, you can solve problems that might be nearly impossible with other methods. Keep practicing with different axis shifts. Whether the axis is above or below the region, the logic remains the same: 2 pi times the average radius times the height. Thank you for learning with us today. You are now ready to tackle shifted horizontal axes using the shell method. Explore more calculus concepts to build your mathematical intuition. This lesson was generated by Vision Solve AI.